Okay, today we will start this chapter which is called multiple linear regression. This is an extension of chapter 11. Nothing new, just the extension of chapter 11. In chapter 11, what we said was, we said y can be written as a function, a linear function of a variable x. We put a lot of restrictions that there is only one variable that is affecting y, which is called x. The relationship between x and y is linear. Epsilon has a normal distribution. It has a zero mean. It has a constant variance. All the epsilon i's and j's are independent of each other. These were all the assumptions. Now, among all these assumptions, there was one of the assumptions that x is the only variable that is affecting y. We are going to let go of that assumption and we are going to define a multiple linear regression model where you have a variable that is affected by many predictors. The example of simple linear regression we gave was where y was your monthly expenditures. And your x was, let us say, monthly income. But the point is that monthly income is not the only thing that is affecting your monthly expenditure. Maybe the family size is also one of the important factors that define your monthly expenditure. Maybe other variables are also affecting the monthly expenditure. There are many known and many unknown variables that are affecting your monthly expenditures. So to accommodate more variables on the right side in the equation, when you are predicting a response variable y, we write down a multiple linear regression model. And that multiple linear regression model is written as y equals the intercept plus beta 1 x1i plus beta 2 x2i all the way up to beta k xki plus the error term. Now, look at the similarity between this blue model and the one I wrote on the top in the red color. There is intercept that is common, there is epsilon that is common, there is y that is common. The only difference is that instead of one predictor, now we have how many predictors?
K.
We have k predictors. So here in this model, the first thing you need to understand is that the number of predictors is denoted by k. So whenever you see this k, this should refer to the number of predictors in the model. So if you have a model with 2 predictors, k will be 2. With 3 predictors, k will be 3. Now, the beautiful thing about this chapter is you don't have to do any calculations. We will provide you the Minitab outputs. You just have to interpret the results. You just need to know what is the meaning of everything. You need to know the relationship between everything, nothing else. No calculations, no computations. You will only be relying on the Minitab output, the one we will provide you in exam. Now let us have an example where I will run the Minitab command for multiple linear regression model. I'm going to run this example with this example 12.2. Let me see if I can find the data for this 12.2. If I have the data, I will run the regression and I will interpret all the results for you. This is the example 12.2. So let me see if I can find the data against this example. There is this 50, 110, 120. So I don't think it is available here. Let me copy it from the book. I think there is a problem with this y variable, so let me write it manually. Nine point 24.45, 31.75, 35, 25.02, 16.86, 14.38, 9.6, 24.35, 27.5, 17.08, 37, 41.95, 11.66, 21.65, 17.89, 69, 10.3, 34.93, 46.59, 44.88, 54.12, 56.63, 22.13, and 21.15. So this is your data on 3 variables. I'll copy this one and paste it in Minitab. And from there, I will copy the output and explain everything with reference to that output. In this example, y is the strength of the wire bond. X1 is the length of the wire bond. X2 is the height of the die. So height of the die and length of the wire is affecting the strength of the wire. So let me paste it. The first variable is y, then there is x1, then there is x2. I'll just simply run the multiple regression model, which you will learn how to run in the lab component. And I will copy all this output. This is what will be given to you in exam. So this will be what is going to be given to you in exam. So let us start with this thing. In this output, what I'm going to explain first is this coefficient part. That's the easiest thing. In this coefficient part, there is a constant that is beta naught. Constant that is beta naught. Then there is a coefficient against x1. This is beta 1 hat, sorry, hat. And the coefficient of x2, this is beta 2 hat. So if I ask you to write down the model, which is already written here, the model is y hat. This is equal to 2.26 plus 2.7443 x1 plus 0.101253 times x2, where y is the strength, x1 is the length of wire, and x2 is the height of die. That is the first thing we interpret from the model. Now we come to the interpretation part. How do you interpret these constants? Again, the interpretation is exactly the same. How do you interpret this 2.26, the intercept? Beta naught hat is 2.26. How do I interpret? The first thing I will say is this is only interpretable if there are practical meanings of x1 and x2 equals 0. Beta naught hat can only be interpreted if x1 equals 0 and x2 equals 0 is practically possible. And if there is practically possible to have x1 equals 0 and x2 equals to 0, then this 2.26 is the value of y when x1 and x2 are both 0. When the length of the wire is 0 and the height of the die is also 0, and practically both of these things are not possible. So in this specific example, because the length cannot be 0, you cannot have a wire with 0 length, you cannot have a die with 0 height. So practically here you will say 2.26, this is not interpretable quantity. In this question, (2.26) cannot be interpreted. Then we come to the second coefficient, 2.7443. This is beta 1 hat. 2.7443. The meaning of this beta 1 hat is that on average, strength increases by 2.7443 units due to 1 unit increase in length, comma. This is the exact same interpretation we did in chapter 11. After comma will be the difference because we have another variable here, the height of the die. So we will keep that variable constant when we interpret this first one, keeping height of the die fixed. So you will interpret this coefficient by fixing the other one, all the other ones. So if there are 2 more variables, you will fix both of them. If there are 3 more variables, you will fix all of the others and interpret one of them. Similarly, your beta 2 hat is 0.01253. So you will say on average, strength increases by 0.01253 units, whatever the units of strength is, due to a unit increase in length of the height of die. Keeping length of wire fixed. So you interpret this one, keeping the other one fixed. This is how you interpret the model. First thing. Once you know how to interpret the model, once we defined the model in chapter 11, what was the next thing we did? Once the point estimation is done, what is the next thing we do? Anyone who remembers, once we defined the model, simple linear regression model, we estimated beta naught hat and beta 1 hat in chapter 11. Once the point estimates were done, what was the next thing we did in the chapter?
Estimate the error.
We estimated the standard errors and moved towards the confidence interval and testing of beta naught and beta 1. So here now you have a model with many slopes, not a single slope. Let me write down the model again. Now you have many slopes. In fact, you have k slopes. You have k slopes. And how many parameters do you have? You have k plus 1 parameters. There is one extra intercept. There are k slopes and there is one intercept. So in total, there are k plus 1 parameters that you estimated. Like when we have two variables, we have three estimators. There's 2.26, there is 2.7443, and there is 0.01253. So always when you have k variables in the model, the number of parameters you have to estimate is k plus 1, because there is one intercept in there in the model. Now, when you talk about the hypothesis test, one of the very popular hypothesis tests in chapter 11 was the testing of beta 1 equals 0. Beta 1 equals 0 means that x is not affecting y at all. X is a useless variable in the model. So here we have many betas. So your interest may be in one of the betas, maybe in some of the betas, maybe in all of the betas. So the hypothesis testing here is not simple. You may be interested in testing one variable. And now I'm ignoring the intercept and I'm only talking about the slopes. So you may be interested in either testing one variable or let's say one coefficient. You may be interested in testing all coefficients at the same time, or you may be interested in testing some coefficients. So these are three different situations that we will discuss in today's class. I'll start with testing one coefficient. If you are interested in testing one coefficient, that's very simple. Very, very simple. For example, you are interested in testing that H0 that beta 2 is 0 against the H1 that beta 2 is not 0. The simple test statistic for testing this one is T, that is equal to beta 2 hat minus beta 2 naught divided by standard error of beta 2 hat. And this standard error of beta 2 hat is given in the Minitab output. What is that? It's given here. The standard errors are given here. Now we come to the second part. The standard errors, they are given in the second column here. So these standard errors are used where? They are used in testing. We use these standard errors in testing. So for the testing purpose, you can use these standard errors. Let us use this standard error and test whether beta 2 is 0 or not. So we will plug everything in. Let me see 0.01253, that's beta 2 hat. So let me plug it in. So this will be 0.01253 minus what is the value of beta 2 I'm in testing in H0? Who can tell me?
0.
0. I'm testing 0 divided by the standard error of beta 2 hat is 0.0028. 0.0028. So the value of T I'm going to get is what? Anyone with the calculator?
5.012.
5.012. And the degree of freedom for this question, we will always be n minus k minus 1. Keep in mind, this is n minus k minus 1. If you remember, the degree of freedom in chapter 11 was 2 because k was 1. So it was n minus 1 minus 1. In general, it is n minus k minus 1. So if you have one variable, it will be n minus 2. If you have two predictors, it will be n minus 3 and so on. So we will reject H0 here. I'm following the rejection region approach. If my T0 absolute value is more than T alpha by 2 with n minus k minus 1 degrees of freedom. So let us say if your alpha is 0.05, your alpha by 2 will be 0.025. And your V will be n is 25 in this question, k is 2 minus 1, so it will be 22. I will go to the T table with 22 degrees of freedom. 22 degrees of freedom. And I will look for alpha by 2, 22 degrees of freedom. And I will look for 0.025 and the value is 2.0739. 2.07, I think 39 it was. So I will reject H0 if my T0 is greater than this one, the absolute value 2.0739, and it is greater than. So I will reject H0 and I will say that beta 2 is not 0. Now, one of the interesting things here is I may be interested in another hypothesis, H0 beta 2 equals, let us say 0.1 against H1 that beta 2 is not 0.1. I may be interested in upper sided hypothesis. I may be interested in lower sided hypothesis. I can do that. Your T will be 0.01253 minus 0.1 over 0.0025. And then you will proceed accordingly. You can test any value, not only 0, you can test any value, but specifically, why are we most of the times interested in 0? because beta 2 equals 0 means that x2 is an insignificant predictor. And hence should not be in the model. If the coefficient of x2 is 0, that means that term should not be in the model. That term should vanish. So mostly you will see we are interested in beta 1 equals 0, beta 2 equals 0, beta 4 equals 0, beta 5 equals 0. And if this hypothesis is accepted, if your H0 is accepted, if your p-value is more than alpha, that means you're in trouble. The variable is insignificant. You should get rid of this variable. And these hypotheses in which mostly we are interested, these are ready-made given in the output here. For testing that beta 2 equals 0, the t-value is already given 4.48. And why is it different from the one we calculated? I think I used the wrong value of standard error. I used 0.0025, I think. Yes, I should have used 0.0028. This is 4 point something. This is already given in the Minitab output. 4.48 is the t-value and the p-value is also given 0.000. Up to 3 decimal points, the p-value is already given. So the p-value 0 means you already reject H0. This p-value is against H0 that beta 2 equals 0 against H1 that beta 2 is not 0. So you have most of the things are already there in the Minitab output. You need some calculations only if you are interested in testing beta 2 equals to something other than 0. If you are interested in 0, that's already there in the output. Now a question. Is x2 a significant variable or insignificant variable in predicting y?
Significant variable.
It is a significant variable because the p-value is 0. P-value is small. If the p-value is small, that means you reject H0, and when you reject H0, you are indirectly saying that beta 2 is not equal to 0. And if beta 2 is significantly different from 0, that means the variable is significant. Similarly, what about x1? Is x1 a significant variable or insignificant variable?
Also significant variable.
It is also statistically significant variable, so it should be kept in the model. So today what we did is we defined a multiple linear regression model. Number one, we discussed how do we estimate the parameters of this model. We said they are coming from the Minitab output. We just run the Minitab and run the command on the Minitab and get the coefficients from there. Then we discussed how to interpret these coefficients, number 3. And finally, number 4, we said that when we talk about hypothesis testing in multiple linear regression, there are basically 3 types of hypotheses we can test. Number 1, we can test the significance of one predictor at a time, one at a time. That will be tested by a t-test. And most part of it is given in the Minitab output. Tomorrow we will discuss how do we check the significance of all the regressors. That means the significance of whole model at a time. We will check that beta 1, beta 2, beta 3, beta 4, beta 5, all of them are 0. Not one by one, all at a time. And then finally we will discuss how do we test some coefficients. That means maybe I'm interested in testing that beta 1, 7 and 9. I want to test these 3 variables. So we will cover this second part in the next class. And if you don't have a question at this point, you can leave the session. Yes, Muhammad Ali.
Doctor, if X1 or X2 was not significant.